Hello, my name is Doohyun Bang, and I'm research scientist for SK Telecom. My advisor, Professor Shim, and I are honored to introduce our work, MGGAN, solving mod collapse using manifold-guided training. To begin with, let me explain the function of generative adversary network, also called as GAN. A GAN is composed of two networks, a generator and discriminator. The model aims to run that generation process based on adversary competition between the two networks. We can imagine the generator as akin the counterfeiter and the discriminator as akin the police officer trying to determine whether a bill is real or fake. The generator attempts to create outputs that are similar to a real one, while the discriminator guesses whether they are real or fake. The result of this Josephson gain fine-tunes the generator until it produces sharp and realistic samples. This status is called Nash equilibrium. In the original paper by Goodfellow et al., the author introduced a minimax GAN, but suggested utilizing the non-saturating GAN for actual implementation. This function is shown in the middle of the slide. Although a GAN produces high-quality samples, its sample diversity is generally poor. This is a well-known issue in GAN training, referred to as a mod collapse. In the bottom figure, this phenomenon becomes evident, as a GAN captures only a single mod out of 8 mods of a target distribution. As a result, it produces high-quality sample for that single mod, but it tends to generate similar sample all the time. Arjovsky et al. Theoretically demonstrated this phenomenon. That is, the generator of non-saturating GAN indeed optimizes the reverse KL divergence. The reverse KL tends to cover partial modes of that distribution, as shown in the top figure. This is exactly the same behavior we see with the mod collapse in GANs. Thus, the question arises, how can we address the disadvantage of GANs? A naive solution could be to use the forward KL property, as opposed to reverse KL. As shown in figure, for the KL tend to cover two modes of Gaussian distribution, but its shape is incorrect. In fact, such a behavior is observed in autoencoder. The autoencoder aims to reconstruct all inputs, and its reconstruction objective can be interpreted as a forward KL as discussed by Vincent et al. As a result, an autoencoder can cover all modes of target distribution. However, because the optimization of autoencoder eventually chooses the average sample as its result, the consequence is poor reconstruction performance like blurred image. In summary, the standard GAN is trained according to adversary loss, so it has a reverse KL characteristic. Hence, a GAN could generate high-quality images, but images will have poor diversity. On the other hand, the autoencoder is trained by targeting reconstruction loss and has a forward KL characteristic. In this case, the diversity is high, but quality is low. So far, we have demonstrated what causes the mod collapse and how it is related to the choice of losses function. We can conclude that there is trade-off between quality and diversity, according to which function is chosen for GAN training. This complementary characteristic of reverse and forward KL inspire us to focus on how to increase diversity without degradation in quality. It is important to note that we are only focused on modifying the discriminator because the generator updates is governed by the discriminator. For that, we modify the discriminator so that it is influenced by both the original discriminator and the proposed guidance network. Then, how could we transfer the forward K property to the GAN? That only consider the reverse K property. First of all, we train the autoencoder, and then we use the encoder for guidance network to extract the forward K features. Please note that we fixed the variable of encoder to guarantee its forward K power. The guidance network is composed of encoder and discriminator. The encoder maps real and fake sample to the manifold space. The discriminator for the guidance network, DM, aims to distinguish whether the encoded features are real or fake. Finally, the two discriminators, dx and dm, determine the authenticity of the input and encoded feature respectively. Since the guidance network learns the forward KL property and the standard discriminator learns the reverse KL property, the generator could learn simultaneously both the forward and reverse KL property. To demonstrate that the guidance network help prevent GANs from missing modes, we tested the network using 8 modes of 2D Gaussian mixture model. In order to investigate how the interval among the modes affect mode collapse, we set the standard deviation to 0.01 and 0.35 respectively. When modes were far apart, that is, with a standard deviation of 0.01, the GAN suffer from mode collapse, whereas other models effectively solve this problem. In contrast, when the modes were adjacent, that is, with a standard deviation of 0.35, the unlearned GAN and VGAN captured almost all of the modes, but generated highly scattered samples that did not accurately represent the true distribution. However, our MGGAN consistently resolved mode collapse with an accurate representation in both cases. Next, we will evaluate the quality of different types of GAN before and after the addition of guided network using the inception score. Our variance consistently score either at baseline or better. As the FID score measures the sample quality and diversity simultaneously, the extent of the improvement in each case clearly demonstrate that the impact of our proposed method. We also examine whether the encoder mapping induced the meaningful manifold space for enhancing diversity. If the generator reproduces more accurate image, that would indicate that it can cover more mode. To access the mode coverage, we devised a new method to generate a reconstructed image using the manifold feature and generator. For that, we built an additional network called a linking network that transforms our manifold space Pm into the latent space Pz to infer the latent vector of real data. For more details of linking network training, please refer to the right column on page 7 of our paper. Odd columns are test images, whereas even columns are the corresponding reconstruction from each model. As you can see, our proposed method reproduces the sample with better quality than the existing bilateral GAN, only. To quantitatively measure reconstruction quality, we employ the PSNR and SSIM as summarized in the following table. We believe that our high reconstruction accuracy on the other subjects support that the effectiveness of our guidance network toward diverse mode coverage. Since we use an autoencoder to extract the forward K features, we might suspect the improved performance came from memorization. We demonstrate it is not the result of memorization through latent space working. Left and rightmost columns that are marked with the red boxes are test images, and just beside them, the one marked with yellow boxes are the corresponding reconstructions. Intermediate columns between them that are marked with green boxes are linear interpolation in the latent space between the reconstructions. In conclusion, we observed the meaningful connectivity of latent space interpolation. And the following are our extended works that are based on the basic concept of MGGAN. Our code is available as this GitHub link, and if you have any question or need more information, please use this email address. Thank you for listening.